One of the first techniques that we are going to learn is called k-means clustering. It's a very elegant approach for partitioning the dataset into k distinct, non-overlapping clusters. To perform this technique, we must first specify the desired number of clusters k, and then the k-means algorithm will assign each observation to exactly one of the k possible clusters. This clustering procedure results from a very intuitive mathematical problem. We begin by defining some notations. Let C1 through Ck denote the sets containing the indices of the observations in each cluster. That means C1 contains the indices corresponding to all the observations that belong to cluster 1. These sets satisfy two properties. Firstly, they must add up to all the observations, because every observation has to be assigned to one of the k possible clusters. On the other hand, the intersection between any two distinct clusters is an empty set. That means the clusters are non-overlapping. In other words, no observation belongs to more than one cluster. For instance, if the ith observation is in the kth cluster, then I belongs to C suffix k. The idea behind this approach is that a good clustering is one for which the within cluster variance is as small as possible. This within cluster variation is a measure, W as a function of Ck, of the amount by which the observations within a cluster differ from each other. Hence, we want to solve the problem that we want to add all the within cluster variations across the different clusters k equal to 1 to capital K, and then we would like to minimize this overall sum. In other words, this formula says that we want to partition the observations into k cluster such that the total within cluster variation, that is summed over all the k clusters, is as small as possible. This algorithm is one of the most popular yet simplest approach. Here is how it works. The first step is to select the number of clusters k that you think is the optimal number. Next, we want to initialize k points as centroids randomly within the space of our data. Then we would like to attribute each observation to its closest centroid based on some distance or similarity measure. Once we have done this step, we would like to update the centroids to the center of all the attributed set of observations. Then we would like to repeat the last two steps until all the centroids are stable. That means once you update the centroids, the location of the centroids do not change. So here is a picture. On the left hand side, we have some unlabeled data. Then we assign 3 points that are marked as centroids on the right hand side as the centroids for this data. Then for all the other data points, we assign them to the centroid that is nearest to it according to some distance, for example the Euclidean distance. On the right hand side, as you can see, the 3 different colors, the green, the blue and the red, correspond to 3 different clusters after the original points have been assigned to the nearest centroid. Once we have the points assigned to the nearest centroids, then we take the average of all the observations in each cluster, and the resultant average becomes the updated centroid. And then we repeat these steps until the centroids become stable. Let us look at some examples next. We are going to look at the iris data. So first of all, here is a look at the data set. We see that we have the sepal length, sepal width, petal length and petal width as the 4 features, and we have the corresponding species as the output. Here's a plot of the petal length versus sepal length. What we are going to do is we are trying to cluster the observations here without taking into account the species column. a classification technique would include the output variable in the training, but here we are trying to cluster the different flowers based on the features only. The function here that we are going to use is called k-means. We are going to use my.iris, which is the variable that stores the features of the iris dataset. And then we are going to use k equal to 3. The reason we have used k equal to 3 is because we know a priori that there are 3 different species, and the function here uses centers equal to 3. Now we are going to compare this cluster with the species label. Notice that cluster 2 corresponds to the Setosa species. The green cluster corresponds to the versicolor, and the red cluster corresponds to the virginica. Let us try to understand the output that we receive when we perform the k-means clustering. First of all, k-means clustering with 3 clusters of sizes 62, 50 and 38 tells us that the computer has assigned these many observations in each cluster. Next we have the mean values of the 4 features for the 3 different clusters. For example, for the first cluster, the sepal length is 5.90, the sepal width is 2.748, the petal length is 4.39, and the petal width is 1.43. Next we have the clustering vector, which shows the cluster labels corresponding to each observation. For example, the 76th observation belongs to the first cluster. Next we have the within cluster sum of squares by cluster. This is the within cluster sum of squares for each of the different clusters. Each observation is allocated to the nearest cluster, and the distance between an observation and a cluster is calculated as the Euclidean distance between the observation and the cluster mean. That means the within cluster sum of squares for observations in a certain cluster C with cluster mean x underscore c bar is summation j equal to 1 to p. Here the summation is over the p different features or the different coordinates of the corresponding vector. xij minus xc comma j bar whole square. So it's a sum over the different coordinates. So at first we take the difference across different coordinates or features and then we square it and add it up for the different features. And then the second or the outer sum is over the different observations in that corresponding cluster. This overall expression gives us the within cluster sum of squares for one cluster C. The 88.4% in the previous output is a measure of the total variance in the dataset that is explained by the clustering. The k-means approach attempts to minimize the within group dispersion and maximize the between group dispersion. By assigning the samples to k clusters rather than n, the clusters have achieved a reduction in sum of squares of 88.4%. But the question is how to get this optimal value of k. One technique to choose the best k is called the elbow method. This method uses within group homogeneity or within group heterogeneity to evaluate the variability. In other words, we are interested in the percentage of the total variance that is explained by each cluster. You can expect the variability to increase with the number of clusters. Alternatively, heterogeneity decreases. Our challenge is to find the k that is beyond the diminishing returns. Adding a new cluster will not improve the variability in the data if there is very few extra information that is left to explain. The total within cluster sum of squares is the tot.within ss in the list returned by the k-mean output. You can construct the elbow graph and find the optimal k as follows. Construct a function to compute the total within cluster sum of squares for a fixed k. Run the algorithm multiple times with different fixed values of k. Create a data frame with the results of the algorithm and then plot the results. So here is an example. Notice that beyond clusters equal to 3, the improvement in the sum of squared distances is not much compared to increasing the value of k. So here the number of clusters is optimal at k equal to 3. Because beyond that we have a scenario of diminishing returns. Here's another example. We have USA arrests in different states based on 4 features, and then we are going to try to cluster the states accordingly. Before that, here's a little online quiz. For 2 runs of k-means clustering, is it expected to get the same clustering results? And the answer is no, because by default, the k-means clustering chooses the initial centroids randomly from the observations, and the final results are going to depend on this initialization. To get rid of this randomness, we use a new feature called nStart equal to 25, which chooses 25 random starts and chooses the best start automatically. So here is the US arrests dataset. We have murder, assault, urban population, and rape. We are going to scale these observations because we are looking at the distances. And we are going to use the k-means clustering with 4 clusters. We have the clusters of sizes 8, 13, 16 and 13. We have the cluster means for the 4 different clusters. And then we have the labels